All right, this is section 3.2, using the second derivative. Right, in section 3.1, we looked at using the first derivative to give us information about the behavior of a function. Right, we could determine where the function was increasing or decreasing, and then we could use that observation to determine where we had relative maximum or minimum values for our function over an interval. All right, so this second derivative has uses as well in terms of what it tells us about the shape of the graph of a function. You can actually use it for a couple of different things. The primary use of it, though, is going to be to determine what's called concavity. Now, the concavity of a graph describes how the graph bends. And you have a couple of examples there, concave up, concave down, in terms of the shape of the graph. And what I always kind of say with concavity to determine, if you're looking at a graph, if you can't tell or you're not sure, take your hand and place it palm down, and then trace the graph or the shape of the graph with your hand. And if your fingers want to bend up, then the graph is concave up. And if your fingers want to bend down, the graph is concave down. And so that's a pretty easy way to tell. But it tends to be a pretty straightforward observation, just as with increasing and decreasing. Also, make another note. Notice if we want a more just graphical observation and relating it to what the derivative tells us. If you look at the tan lines to your curve, right, in each of these cases, say this one on the left, if I were to draw tan lines to this curve, right, every tan line that I would draw, right, that touches that curve at one point lies below the curve, in the case that the graph is concave up. On the other side, if we draw tan lines to the curve that's concave down, notice all those tan lines lie above the curve. All right, so that's actually the formal definition of concavity. It has to do with where the tan lines to the curve lie. If the tan lines lie below the curve, the graph is said to be concave up. And if the tan lines lie above the graph is said to be concave down. That's the formal definition. Right? Our more useful definition is just to make an observation about the shape of the graph, and then we're going to use the second derivative to give us that information. Right? So we have our theorem. We'll call this the test for concavity. If the second derivative, if f double prime is positive for all values of x in an open interval I, then f is concave up on that interval. And if f double prime, if our second derivative is negative for all x in that interval I, then f is concave down. So again, it's a pretty straightforward observation. Just like we used our first derivative to tell where the function was increasing or decreasing, right? It was positive if the first derivative was, or increasing if the first derivative was positive, decreasing if the first derivative was negative. The second derivative tells us about the concavity. If the second derivative is positive at a value, then we're concave up. If the second derivative is negative, we're concave down. So of course, obviously, you have to keep them separate as far as which derivative gives you which information, right? Not to get those confused. Inflection points. An inflection point is a point at which the graph changes concavity. So if we're changing from concave up to concave down, or from concave down to concave up, we have what is called an inflection point. We label that as x sub 0 or x naught, and we used that notation before, but we'll just call it x sub 0 in this case. Now, these inflection points can only occur where the second derivative is either 0 or where the second derivative is undefined. It is very much similar to what we had with those critical values for the first derivative. Right, we found where the first derivative was 0 or undefined. Those we called the critical values of our function. And then we said those were possible locations for those relative max or relative min values. And then we would set up our little test strip and we would check the sign of our first derivative to tell us where it was increasing or decreasing. And then we could make that observation about relative max and relative min. Exact same process here with concavity and inflection points. So, but we do it with the second derivative. So where the second derivative is either 0 or undefined, we have possible inflection points. But just like we did with our first derivative, we'll have to set up a little test strip, and then we check the sign of our second derivative over each of the intervals determined by those possible inflection points. And then if you have a change in concavity on either side of that value, then it is an inflection point on the graph of our function. Otherwise, it's not, so it's just a value that we would have to test, just like those critical values with our first derivative. Now, I told you that there were a couple of different uses for the second derivative. Second derivatives can also be used to determine relative maximum and relative minimums. Right now, we typically don't use this a lot, though, because we have our first derivative that works perfectly fine for that. We find our critical values, check the values or the signs of the first derivative on the intervals, increasing, decreasing. You could also make a determination about relative maximums and minimums with our second derivative. If we let x equals c be a critical value, right, so we first find our critical values, we have a relative minimum at c, or at f, at the value f of c, if the second derivative is positive. And we have a relative max if the second derivative is negative. Right? Think about what that tells you. Why is that the case? Because if the second derivative is positive, we know that the graph is concave up. And if we have a critical value, right, then we know our function would be, or that point would be, a relative minimum. Right? In the case of a relative max, if our second derivative is negative, right, we know the graph is concave down. And so at that critical value, you would have to have a relative max. So there's our concave up. Has to be a relative minimum. There's our concave down. Has to be a relative max at the critical value. But like I said, we don't typically use that test. I mean, it's another option for determining relative max and mins. The first derivative works just as well. Probably, we have to have the first derivative anyway to get to the second derivative. So we use the first derivative to test for relative maxes and mins, increasing and decreasing. We use the second derivative to test for concavity. And again, it does give you another option, another way that can be done. So here's an example, and this is going to kind of combine the things that we did back in section 3.1 with what we're doing in this section with concavity. So this obviously makes a really good test question. All these different parts, determining the critical values, critical points on our graph, where the function is increasing or decreasing, where the function has relative max or mins, and then now the second derivative, finding possible inflection points, determining concavity, where is it concave up or concave down, do I have an inflection point, and then also kind of mention, sketching a graph or using that information to sketch the graph, because ultimately this is all information that's used to give us an idea of what the graph of the function looks like, right? What the behavior of the function is. It's all about function behavior. We keep coming back to that when we're using or talking about derivatives. And now we're doing it in the context of the shape of the graph, right? And what that tells us about the behavior of the function. So the function that we're looking at, number one, I've got f of x equals x cubed minus 48x minus 1. I'll go ahead and find our first and second derivative because we'll need to use both of those. So our first derivative, and this is a nice little polynomial, power function, power rule. So f prime would be 3x squared minus 48. And then our second derivative, f double prime, would be 6x. So then we'll start first by finding our critical values. Remember, our critical values come from setting our first derivative equal to 0. So I'll take the 3x squared minus 48. Let's see if we can make that a little less fat. Right. And then we're setting that equal to 0. Right? So remember, that's how we're finding those critical values. And then we're solving that equation where we could factor out a 3. That gives me x squared minus 16. All right. And then x squared minus 16 equals 0. You could either factor that or you could, use square root property either way. But that's where our positive and negative 4 are coming from. Right? So x equals plus or minus the square root of 16 or positive or negative 4. Right? So there's our critical values. And those we're going to use with our first derivative. All right, to determine or to set up our little test strip and then determine where we're increasing or decreasing. Our second derivative 6x, right, we set that equal to 0. That's how we get our possible inflection points. And if I set 6x equal to 0, then I've got x equals 0. Right? So, of course, keeping those straight. First derivative, setting that equal to 0, what does that find? That finds our critical values, which we then use to determine where the function is increasing or decreasing. Do we have a relative max or relative min at those values? Or neither. Second derivative is used for concavity, right? So setting the second derivative equal to 0, finding our possible inflection points, and then we'll use our test strip with the second derivative to determine where it's positive or negative, where we have concavity, up or down. So part A, we were asked to find the critical points. Remember, the critical points are the actual points on the graph. So it's a little distinction in the terminology. Critical value, those are the x values where those relative maxes or mins could possibly occur. The critical points are the actual points on the graph. Right, so I went ahead and plugged 4 and negative 4 into our function. So again, we're working with a bunch of different functions here. The original function, the first and second derivative. So be careful as far as which function you actually plug those values in. If I want a point on the graph of my function, plug it into the original function. So f of negative 4, I get 127. F of 4, I get negative 129. So those would be critical points on the graph of our function. Part B, we're asked to determine intervals where f is increasing or decreasing. So that's again what we did back in section 3.1. So finding our critical values as we did, negative 4 and 4. Set up our test strip. And then plug in those test points in each of the intervals. So I plugged in negative 5, 0, and 5. F of negative 5 gave me a positive value. F prime of 0 gives us a negative value, and f prime of 5 gives us a positive value. So again, that's our first derivative. We're increasing where that first derivative is positive, so increasing on the intervals from negative infinity to negative 4, and from 4 to infinity. And then we're decreasing where that first derivative is negative, which is that interval from negative 4 to 4. We can then identify relative maximum and relative minimums, right, where we have a sign change in our first derivative. So we have since we're increasing on the left of negative 4, decreasing on the right of negative 4, we have a relative max at that point where x equals negative 4, or at the point negative 4, 127. Since we are decreasing on the left of 4 and increasing on the right of 4, we have a relative minimum, right, at the point where x equals 4, or at the point 4, negative 129. And again, now that's exactly what we did back in section 3.1, so that's not new. Going forward, though, parts D and E dealing with the concavity and the inflection point, so that's our second derivative. If I can hit the right thing up here. All right, so taking our second derivative equals 6x, and then we found our possible inflection points by setting that equal to 0. So where x equals 0. And then we follow the same procedure we followed with our first derivative. We set up a test strip, and then we test values in each of the intervals determined by that test strip. So I plug in a value to the left of and to the right of 0. F double prime of negative 1 gives me a negative value. F double prime of 1 gives me a positive value. And just like with our first derivative, so all we care about is the sign. I don't care about the value. It's all about whether it's positive or negative. That gives me the information about concavity in this case. So since we're negative on that interval from negative infinity to 0, our second derivative, then we're concave down on that interval. And since the function or the second derivative, make sure Again, be careful as far as which function you're talking about. So this is f double prime. Since our second derivative is positive on that interval from 0 to infinity, then the graph would be concave up on that interval. And so inflection points would occur at any point where we have a change in concavity. So since we're concave down on the left of 0, we're concave up on the right of 0, then we have an inflection point at x equals 0. And if you plug 0 into your function, so again, the point on the graph is the value plugged into the original function, f of 0 will give you -1. And then the graph that I have there kind of gives you a sketch of what a possible sketch of the graph of that function, right? Or generally what the graph of that function would look like. Right? So we're concave up, or scratch that, just moving from left to right. We were increasing on this interval from -infinity to -4, and then we're decreasing on -4 to 4. But also in that, notice we're concave down on this part until we hit 0, and then our graph changes to concave up. All right, so follow your hand along the graph. When I follow along the concave down, my fingers are curling down, and then when I hit that point 0, -1, my fingers want to bend up, and I change to concave up. And then when we hit 4, our function is increasing. Right? So it's just moving from left to right. That's why we had to go ahead and identify the points on the graph at -4, 127, 0, -1. And 4, -129. And then you just move from left to right along that graph, changing whichever characteristic we need to change when we hit each of those important points. Right? So at -4, we changed from increasing to decreasing. At 0, we changed our concavity from concave down to concave up. And then at 4, we changed our graph from decreasing to increasing. Right? But at least with that, be able to identify the graph. So if I give you a choice of graphs, could you pick the graph that would match the graph of the function? Obviously, you can just graph it on the calculator, to see the graph. But that's how we use those derivatives to just give us that general information about the shape of the graph. A couple of other examples, just some different functions. Right? So that first example was just with a nice polynomial, nice power function. So number 2 is a log function. Right? F of x equals natural log of x squared plus 16. So again, I'm just finding our first and second derivative, so we can use those to find our relevant information. So f prime. Now remember, we're differentiating a log function here. Our natural log function, the derivative is the derivative of the argument, which is x squared plus 16. So that's 2x over the argument itself. Okay. So the derivative of the argument over the argument. And then to get our second derivative, we're differentiating f prime, we have to use our quotient rule. So since f prime is 2x over x squared plus 16, we have our low d high minus high d low over low squared. And then I went ahead and simplified that numerator. That would give you 2x squared plus 32 minus 4x squared. And combining like terms, I get our second derivative, which is -2x squared plus 32 over x squared plus 16 squared. Right. Second derivative. All right, and then getting our information from each of those derivatives. So for part A, we first find our critical values. We want to find the critical numbers, or the critical points on our graph. So we start by finding our critical values, which again is where the first derivative is either 0 or undefined. Because this time we have a fraction. Where is f prime 0? Well, if you have a fraction, it's wherever that numerator is 0. So I've set 2x equal to 0, and I get x equals 0 as a critical value. Where is that function undefined? Well, that would be wherever the denominator is equal to 0. But notice in this case, x squared plus 16, Where is that going to be equal to 0? Well, that's never going to equal 0, because I don't care what you plug in place of x. The fact that you're going to square it gives you a positive value, always. And then you're adding 16 to that. So you're always going to get something positive there, which means it's never going to be 0. I mean, you could solve it, set x squared equal to negative 16, right? But that's going to give you an imaginary solution. No, we don't have imaginary points on our graph. So yeah, an observation there as far as the value of that denominator. So that leaves me then with only 0, or x equals 0 as the only critical value. And we plug that into our function, f of 0, you get 2.8 approximately. Well, actually, that would be an exact value. And so I have this point 0, 2.8 as the critical point on the graph of our function. All right, so then increasing and decreasing, part B. So we'll take our critical value 0, set up our test strip for f prime, plug in our test points. I plugged in -1 on the left of 0, I plugged in 1 on the right. Plug in -1, you're going to get a negative value. Now, again, like I did with the polynomials, you could look at the sign of the numerator, sign of the denominator, and then what does the quotient give you? Or, again, just take the derivative, take f prime, plug the number in, see what the sign of that value is, positive or negative. You plug in -1, you'll get a negative value. You plug in 1, you'll get a positive value. Now, again, I'm plugging that into f prime. So that gives us a function that is decreasing on that interval from -infinity to 0 because f prime is negative, and increasing on the interval from 0 to infinity because f prime is positive. And since we do have a change in that behavior, right, we're changing from decreasing to increasing at x equals 0, then we do have a relative minimum at that point, at 0, 2.8. Second derivative for our concavity, so f double prime, where is that equal to 0? Now again, our second derivative is also a fraction, so where the numerator is equal to 0 is where that second derivative would equal 0, and where the denominator is 0 is where that would be undefined, right? But just like with f prime, our denominator is x squared plus 16, in this case squared, that's never going to be 0. That's always going to be a positive value. So there are no points where that second derivative is undefined. But we do have the numerator, negative 2x squared plus 32, and where is that equal to 0? Setting that equal to 0, solving that equation. And again, I don't have this in detail, but you could factor out of my way. And let's go over here on the right. I've got negative 2x squared plus 32. I could factor out the -2. Leaves me with x squared minus 16. Right, we factored out the negative, so we have to change that sign. And then, just like the previous example, we have x squared minus 16 equals 0. And this time I'll go ahead and write that out in factored form. So again, either way, but that is difference of squares, x plus 4, x minus 4. And then we set each of those equal to 0, and I've got x equals -4 and x equals 4. All right, so you could do that either way. Bottom line, now these are where the second derivative is 0, so those are, we're saying, are locations of possible inflection points. Right, so at x equals positive or -4. So we set up our test strip, plug in our test values, f double prime of -5. Again, I'm plugging it into the second derivative this time. Plug -5 into f double prime, you get a negative value. I plugged in 0, which is in that interval between -4 and 4. You get a positive second derivative. And I plugged in 5 into that third interval to the right of 4. And you get, again, a negative value. So where that second derivative is negative, we're concave down, which would be then on that interval from -infinity to -4. And on that interval from 4 to infinity. And then we're concave up on the interval from -4 to 4, which is where that second derivative is positive. So then in terms of inflection points, we said where we have a change in concavity, since we're changing from concave down to concave up at -4, then we have an inflection point at -4. Since we're changing from concave up to concave down at 4, then again we have a change in concavity. We have an inflection point at the point where x equals 4. And then I just plugged each of those into our function. Again, if anytime I want the point on the graph, I'm plugging that back into f. So I'm looking at f of -4 is 3.5. As well as f of 4. All right. So again, just be careful. That's always the mistake that I see with this. You're working with the function, you're working with the first derivative, you're working with the second derivative. Just be careful in terms of which function you actually plug the values in. All right. If I want a point on the graph, I'm plugging it back into the original function. If I'm determining increasing and decreasing, I'm plugging it into the first derivative. If I'm determining concavity, I'm plugging it into the second derivative. Okay. And then there's just a rough sketch of the graph of what that function would look like. We said at -4, we changed concavity. At 4, we changed concavity. We also said we were decreasing on the interval from -infinity to 0. So here's a graph that is decreasing on that interval from -4 to 0, but also notice we're changing concavity here at -4 from concave down to concave up. And then at 0, we changed from decreasing to increasing on the interval from 0 to infinity. And again, we had to change concavity at 4 from concave up to concave down, right? But again, you can graph these on the calculator, and I'm just giving you an idea of how we can use these to sketch graphs or give us, again, the idea of what the graph of a particular function looks like. Okay? Number 3, and that's just, it would be an example of taking, or kind of going in the opposite direction now, taking the information and actually sketching a graph. And I actually need to make a correction on that. Let's say we're increasing and concave up on the interval from -infinity to 2. And let's say decreasing and concave down, change that on the interval from 2 to infinity. I meant to change that, forgot. Notice a couple of scratch outs on here. I don't have any white out at home. You know, we're low tech, right? So yeah, just make that correction. But this is, you know, and you'll see some of these in the homework where they'll give you the description and say, here, match the graph, or pick the graph that matches this behavior or has this behavior. So we're increasing and concave up on the interval from -infinity to 2, decreasing and concave down on the interval from 2 to infinity. And so you're going to have to pick a graph that matches that description. Lastly, application, right? We always throw in an application to put this into context a little bit. So for this one, number 4, we've got a new product that is introduced into a market with 150 million potential buyers. The unit sales of that product is given by that function S equals, with all our nice funky decimals, where S is the total sales in millions of units, and X is the number of months after the product was released. S, total number of units in millions, X, number of months after the product was released. Question, find the point of inflection on the graph of that function and interpret its meaning. All right, so I mean, finding the inflection point is not the issue. We can find S prime. Now again, even though we have nice funky decimals here, this is still just a basic power function. So I'm using power rule to find S prime and then S double prime. All right, so nothing fancy there, we just have funky numbers. Then, since I'm looking for inflection points on our graph, we take our second derivative and set that equal to 0 to find possible inflection points. And if you solve that equation, you do get x equals approximately 16.82. I just rounded that to a couple of decimal places. So then we use our test strip, right, to determine where the function is concave up or concave down, I plugged in 16 and 17, which are on the left and right of 16.82. And if you plug 16 into f double prime, you get a positive value. You plug 17 into our second derivative, you get a negative value. So that means our graph is concave up on the left of 16.82, concave down on the right of 16.82. Now, what does that mean in the context of the application? Right? Well, again, what does this function tell me? S is the total sales in millions of units, X months after the product was released. So then what does S prime tell you, right? S prime is the rate of change in S. So S prime is the rate of change in the sales, right? How your sales are changing, whether sales are increasing or decreasing. What does S double prime tell us? Well, S double prime gives us the rate of change in that rate of change of sales, right? So maybe my sales are increasing, but or the amount of sales are increasing, and maybe then the rate of change is changing, and that the rate of sales increases or the rate of sales itself decreases, but still with positive rate of sale, or vice versa. And same thing with negative. We could have decreasing sales where the rate of change in that is either increasing or decreasing. Maybe the rate of change is the change is slowing or increasing or speeding up, I guess would be a good word there. So what does that tell us in the context of what that second derivative or that the information gives us? Well, if it's positive to negative change in the first derivative, since the first derivative is the rate of change in sales, the second derivative, the rate of change of the rate of change, right? You could also then put this simply in the context of what if S, our function, tells us the amount of sales, and then our derivative tells us the rate of change in that. Just as with S and S prime, if S changes, or if, back up, if S prime changes from positive to negative, that means S has a relative max, right? Well, if S double prime changes from positive to negative, then that would be a location of a max for S prime. Right? So, I mean, it's always relative to the previous function. S prime tells us where S is increasing or decreasing, max or min. S double prime, yes, it gives us the information about concavity with respect to S, but it also tells us where S prime is increasing or decreasing. And since we're increasing on that interval up to 16.82, we're decreasing on the right of 16.82, then S prime would have a maximum at that point. And since S prime is the rate of change in our sales, that gives us, or what it's telling us is that we have a point at which the rate of change in the sales has reached its maximum or has been maximized, right? So the rate of change in the sales is increasing, it hits a maximum, and then the rate of change in the sales starts to decrease. Now, not necessarily the sales themselves. The sales themselves could still be increasing, but the rate at which the sales is occurring is decreasing, right? I say that 3 times fast. And so, yeah, interpreting the information, we said that's always the deal with these guys, not just, finding the derivative is not the issue here. What is it actually telling me? What is the information that I'm actually getting from that? And we're going to deal a lot more with that going forward. I mean, we have a lot more application stuff to do in this chapter, and using that derivative to give us actual information about the situation, right? So, yeah, find the derivative. What does it mean? First derivative, second derivative. Okay. All right, that'll be it for this section then. That is section 3.2. See you in 3.3.